Welcome everyone to another National Graphene Association and National Graphene and 2D Association interview. Today we are joined by Adrian Nixon. Adrian Nixon is the owner of Nixene Publishing. He's a fellow advisory board member for NJ2D, and he's also an advisory board member for the International Space Elevator Consortium, which is why we're here today. We're here to talk about graphene in the space elevator. Now, it's a bit more of a niche application, something that might not get as much coverage, something that's definitely for down the line and not in the right here and now. However, it's a very interesting high-tech, future sci-fi application that we could actually see graphene in. So I will let Adrian do the talking on this one because he is an expert on this area. So Adrian, first off, because we talk about space elevator, some people probably heard about it. Some people know what it is. There's going to be people out there who don't know what it is, and some are going to say that it's sci-fi nonsense. So, for those who don't know what the space elevator is, basically, what is it? How would it work? And why is it something that could be important in the future?
Right. Currently there's one way of getting into space, and that is you climb on top of a rocket that's filled with highly explosive, dangerous fuel. You set it off, and it's loud and noisy and hot, and eventually you'll end up in orbit. And then to get back down again, it's the same process in reverse. Everybody knows it's noisy and hot and dangerous coming on the way back down. So that's how rockets work. About the same time that rockets were invented, probably just over 100 years ago, or space rockets anyway, then there was another idea which was around, which is called the space elevator. And there was a guy called Konstantin Tsiolkovsky, a Russian physicist, and he developed what's called the rocket equation, which is basically you need an awful lot of energy and mass to take you up into space, and he can calculate all that. He also came up with the idea of a space elevator, and I think it was from looking at the Eiffel Tower that was being built around about the same time. And he thought, well, what if you carried on building a tower and just kept building it higher and higher and higher? Would you eventually get into space? And then you could put an elevator inside or a staircase, and you just climb up, you'd be in orbit. The problem was when he actually sort of thought it through, the materials let him down. So iron, if you carried on building, eventually crumples under its own weight and the whole tower collapses. Or if you could make something strong enough, it would weigh so much that it would squish into the ground, no matter how hard it is, and sink. So there's a lot of problems there. Then a guy who you'll be aware of, Arthur C. Clarke, a science fiction writer, but also quite a respected physicist, worked on radar in the Second World War. And most viewers would probably be familiar with the film 2001: Space Odyssey. He wrote that. And the film was based on his work. He came up with the idea of a space elevator, which was, very simply put, if you and I are standing on Earth at the minute, and we put a geostationary satellite into orbit above us. So what happens is the satellite is turning at the same speed the Earth is turning. So from our point of view, it's always directly above us. So the idea is, if you took a cable and dropped it from the satellite all the way down to the ground, it would come down directly above me. I can then grab hold of that cable, climb up like Jack in the Beanstalk, and I'd be in space. That's how the space elevator works. Simple, eh?
Simple principle.
Now, most people think it's science fiction, and it sort of has been. And if you'd have asked me 10 years ago, is the space elevator science fiction? I would have probably said, yeah, probably. NASA looked at this around the turn of the century, which sounds a long time ago now. Just around the 2000s, they had something called their Millennial Challengers. And there's a department of NASA called the NASA Institute of Advanced Concepts, NIAC. And they commissioned a feasibility study by a guy called Dr. Bradley Edwards, rocket scientist, quite well-respected guy. And they said, look, go away and have a look at this space elevator thing and come back and tell us, is it actually possible, or is it really just science fiction? So Brad Edwards went away with a few $1 million from NASA and interviewed the world's best researchers in this area, material scientists, engineers, rocket scientists. They took apart all the different components, and basically it breaks down into, you have a bit on the Earth, so there's some kind of base station. You've got something up in orbit up there, which is called an apex anchor. You probably have something at geostationary orbit, which is like a space station. And then you've got the material tether that connects everything together, the rope, if you like, that dangles down. And then you've got the elevator cage that climbs up and down the tether. Brad Edwards went away and found everything on the ground is doable. All the operations stuff, the organization, everything else that manages this vast project is doable with today's technology. The space stuff is all doable with today's technology. The climber or the elevator cage, which goes up and down, that's all doable with today's technology. The only thing which wasn't doable at the time is the material to make the tether out of. And that is probably something which we'll talk about in a minute. But basically, you have to have something which is incredibly light and incredibly strong. And that didn't exist roughly at the time. The closest thing was carbon nanotubes. But the problem is, as you and I know, they can only be made that long.
Yeah. I'm going to say, so that leaves it quite open for the next question of where is it that in the space elevator scenes you're involved, is it likely that we're going to see graphene?
A big clue in what I've already been talking about, eh?
Yeah.
Yeah, there are two, well, there's a myriad of places that this could be used in. So the space elevator is not a trivial project. It is doable. That's something important to sort of get across. But what we're talking about here is probably the biggest civil engineering project ever. But that doesn't mean it can't be done. Where graphene would actually get involved is the material to make the tether out of. So the way a tether works is different to the way elevators work inside tall buildings. So in tall buildings, you've got an elevator cage that you step into, and then they're connected by what are called ropes. There's a number of them, but let's just think of it as one for the sake of argument. And that rope moves; it gets pulled up and wound up onto a drum at in the building, and that pulls the elevator cage up and down. A space elevator works slightly differently. A tether is a continuous piece of material that goes from space all the way down to the ground, and that stays still, it doesn't move. And the elevator cage or the climber grips the tether and then it pulls itself up. And there are a number of different ways that can do this, and ISEC engineers are working on different options. But basically, the piece that's important is the tether material. And now, if you think about the properties it's got to have, just imagine a thought experiment. So you're standing on top of an infinitely high cliff, and you've got some of the world's strongest material in your hand, let's say high tensile steel. So you're infinitely strong as well. So you're paying out this piece of steel over the edge of the cliff. And as it's dangling down, as you pay out more and more, there's that material that dangles down has mass. And the longer the drop, the more mass it has. And eventually the bit you're holding onto will break when the weight of the stuff that's dangling down overcomes its own tensile strength. So materials have to be very, very light and very, very strong. Now, it turns out that pretty much all the strong materials you can think of, Kevlar, high tensile strength steels, they're not strong enough to do the job. However, graphene and some of the 2D materials are actually strong enough and light enough to make this a reality. So it is actually possible, theoretically, and as we move forward with the graphene and 2D world, increasingly looking likely that we could actually make this material. Does that answer your question?
Yeah, it does, and it kind of answers my next one about the characteristics of graphene that make it suitable. Obviously, there's the lightweight and the tensile strength. Is there anything else beyond that, or is it just the physical properties?
Really good question. Graphene itself, because it's electrically conductive, if you layer it up, then as well as being strong and light, so you make a tether from lots and lots of layers of this stuff all stuck together. But if you think about, we'll talk about strengths probably a little bit later, but one other thing you need to think about, the elevator cage that goes up, or the elevator itself, as it goes up through the Earth's atmosphere, it passes through radiation bands, the Van Allen belts and things like that. And so it'll be subject to a lot of radiation. Now, if you're in a rocket, you're moving very, very fast. So you're hanging around in the high radiation area for a very short amount of time. But the elevator won't move as fast as a rocket can. And so it's hanging around in this high radiation area for a long time. Graphene, because you can multi-layer it up and being very light, it's also, it will block a lot of radiation. So pretty much all, actually. So another use for graphene is protecting the occupants and any goods inside the elevator on the way up through the dangerous bit.
How long would it actually take from do they think, for the elevator to go from Earth to space on such a tether?
Yeah, it depends. This is an area of debate at the minute. It depends how fast you can make the crawler go. So I reckon it could probably be made to go very, very fast. But let's say, for the sake of argument, at the minute, we've got about 200 kilometers an hour. So that's just going vertically.
Yeah.
So that's the current sort of best guess based on technology. But I reckon we could go faster than that. To get from the ground up to Earth's orbit, then you're probably talking about maybe a week. So it's quite a while. So somebody once described hell as being stuck in a lift with your friends. You need a lot of distractions. Yeah. So what you would use the space elevator for in the early days would probably be more as a goods lift or goods elevator than a people elevator. Yeah, until you get the speeds up. But that will give you a rough idea at the minute.
Are they just looking at one elevator up and down, or are they looking at simultaneous for up and down?
There are lots of different designs out there at the minute. It's looking like once you build the first elevator, the second ones because you know how bridges are built, you send across a little rope to start off with, then a heavier one and a heavier one. It's a similar sort of thing. You could think of the space elevator as being a bridge to the stars. So once you've built the first one, what you will probably do is build a construction elevator that would make the next one and become a goods lift then for all the material you have to take out the second one. So once you've built the first, then the ones that come after it are relatively easy things to do. Okay. There's a huge amount of engineering challenge to be solved. As any engineers watching this will be going, oh my God. But it is a question you need to ask yourself, if anybody's got that reaction, is, do you think this is really impossible now, given the state of the material science that we're seeing being developed?
It's a good point. Thought-provoking point. And I say there's a lot of advanced materials, a lot of advanced technologies nowadays.
And it's moving fast, as you and I know.
That wasn't even here 10 years ago. So,
yeah.
Technology advancing at a rate not seen before. So,
Yeah.
Who knows what's actually possible in the next few decades, to be honest.
Exactly, yeah.
So switching, back, to graphene. Mm-hmm. And here's a question: how much graphene would it actually take to build, such a tether? And as we know, there's different types of graphene. So what type of graphene would we need to build, such a tether? Because a lot of it's all like little small nano-sized sheets and flakes, and that's how much we're going to need, and what type of graphene will we need for it?
Right, really, really good question. I like talking to you, Liam. Smart stuff. Yeah. So you're quite right. Most viewers will be aware of graphene. Some will be aware of the different types of graphene. So it's worthwhile doing a quick recap. As Liam just said, there are nanoplates of graphene. So that is bits of graphene in liquids. Graphene nanoplate, there, so you can see it's graphene. Or this one here, this is graphene powder. Neither of those would make a space elevator tether because they're little bits of graphene. Although it's 200 times stronger than steel, none of the little bits are connected up together. You can make polymer composites with this, but even that isn't strong enough. They would probably make Kevlar stronger, but still not strong enough to make graphene. So you would need continuous sheet graphene. Now, you and I, Liam, know that you probably recognize this.
Yeah.
This it looks like copper foil, but actually Liam and I know that there is a 1 atom thick layer of graphene on the surface of that copper there. And that's the current state of the art of making graphene. Now, the problem is here that this graphene here, although it's 1 atom thick and covering the surface, the other thing most people don't realize is it's called polycrystalline. So although the graphene covers the surface and it's 1 atom thick, it's not continuous yet. So the continuous graphene is that would be required is called single crystal graphene. That's a perfect single molecule covering the entire surface. And That's called CV. We know that this is CVD graphene, don't we, Liam?
Yeah.
Yeah, chemical vapor deposition. And this is made by a company in California at the minute. But there are other companies that make this stuff. Now, then you've got to get the graphene off the surface of the metal, and then you would end up with a sheet of graphene, which if we magnified it up, then you would end up with something like this. And this is the carbon atoms, the black things, and the bonds between them. And it's incredibly strong. Now, you would think single crystal, that means a single molecule which goes all the way from the surface of the Earth out 100,000 kilometers into space, one molecule. It's a bit of a wild idea, that, because you're a chemist, Liam. Yeah. You know about molecules and stuff. That is quite a big stretch of the imagination to make something that big.
It's a very long scale, to be honest, for any kind of molecule, you know.
Isn't it? Yeah. Normally, you'd think molecules are measured in nanometers, so they, you know, even big ones.
Yeah.
So they're tiny, tiny things. You know, a nanometer is a millionth of a millimeter. And so it's it is a millionth of a millimeter. So it's tiny stuff. But you and I, Liam, know that about 3 years ago in China, at Peking University, they made something called single crystal graphene on copper foil, we've just seen, but they made it about 500 millimeters long. Yeah. So we know that there is a single molecule of graphene that's already been made that long, 500 mil long. So we know it's possible to make single crystal that big, and there's no reason why you just can't keep on adding to it and keep on making it. So in principle now, there aren't any barriers to actually making this stuff big and fast. Yeah. Now the question you asked was how much would be required. So let's have a think about this. If we assume a tether is going to be about 1 meter wide, and it's made up of single crystal graphene. So let's assume that we can make this stuff in rolls and have graphene molecules going up into space, meter wide, 100,000 kilometers long. So that's 100 millimeters long, something like that. This is big. Bear with me. So if we got that 100,000 kilometer long single molecule, meter wide, how much does it weigh? Well, if you look at the density of graphene and run a calculation, you'd find that one layer of graphene going from the surface of the Earth right out 100,000 kilometers, that weighs 77 kilograms. So it's actually not that heavy, really.
No,
you
it's lighter
take
than
one
me.
layer up into space, drop it down. 77 kilos isn't that bad. The problem is you wouldn't just use one single layer. You'd need lots and lots of layers layered up. Now, the people I'm working with at ISEC, the International Space Elevator Consortium, it's great because I get to work with rocket scientists. These aren't mad people. These are guys that have done proper rocket science, so they know what they're talking about. And they've run some calculations looking at the engineering required, how many layers we required with safety margins and everything else involved. And we reckon there's probably something like 12,333 layers to carry something like a 10-ton crawler going up.
Okay.
Even that, so we've got 12,000 layers and each weighing 77 kilos. So we're probably looking around about 950 tons of material to make the space elevator tether. Now that might sound a lot, but if you think about it already, there are already 420 tons of material on the International Space Stations orbiting the Earth already. So we know we can get that type of material, that scale of material up into orbit fairly quickly. And we don't need to use rockets once we've started to build the construction tether. Once it's strong enough to hold the weight of a service elevator, then it can go up and start taking material up so it can work with rockets. The interesting thing is here, it's important to say that the space elevator is not a competitor for rockets, it's complementary.
Yeah.
So if you want to get into space fast, use a rocket. If you want to get into space slowly, reliably, probably boringly, but and take lots of material up, you need a space elevator.
No, I'm gonna say so.
A long answer to a short question.
Yeah, I'm gonna say there's a lot of difference. It's obviously talking about making single crystal graphene. Basically, you know about making on such a huge scale. These are like major challenges. Obviously, that's going to be one industry challenge to overcome, is like trying to make something on this size, this scale, and at such a high quality that it's not going to cause any kind of defects. which, let's face it, could have catastrophic consequences if you have something full of defects in such an application. So beyond essentially trying to manufacture and design a new material at huge scales, is there any other major industry challenges that are going to need to be overcome within the graphene industry to make an application such as this a reality?
Yeah, a list as long as your arm. This is the biggest civil engineering project of all time. Probably covering areas that nobody's ever thought about. It will go all the way. You need to pay attention to things down at the nanoscale. So you and I are aware of the work that goes on at the NGI with the Nobel Prize winners and things like that. We need to be aware of their work down at that 10 to the minus 9 of a meter. But also we need to be right up at the other end, looking at 10 to the 8 meters, that sort of scale as well, and everything in between. I mean, this is unheard of. You mentioned about the quality required. Yeah, we're going to do very, very high quality. If we run, the industry standard at the moment is something called Six Sigma production, which means you've got 99.99 something percent of good production, but there'll be a tiny amount of defects. Even if we applied Six Sigma production techniques to this, we'll probably end up with about 350 meters of defects somewhere in the tether. So we've got to completely rethink what we think of as quality there. Also, when I talked about the number of layers, you'll probably have heard me say that the ISEC engineers put in a 40% safety margin. That's because we're taking a view that we can't eliminate all the defects, therefore you build in safety margins into all your calculations right now. So that's one of the challenges. The other challenge is nobody's ever taken something and dangled it from orbit all the way down to the ground before. There'll be things that we haven't thought of. Weather has been thought about. Also, where would you put it on the surface of the Earth? So here I have the Earth in my hand. The way that the space elevator works is if you imagine you're familiar with a yo-yo from childhood, Liam.
Oh,
you've
yeah.
got to on a piece of string.
Yeah.
If I was spinning around in my chair and spinning round, then the yo-yo flies out sort of sideways, and centrifugal force keeps it out. Yeah.
Yeah.
Whereas if I put it above my head, it would if I threw it up, it would land back and bounce off my head. It's the same thing with the Earth. You don't put a space elevator here, you put it at the equator so it spins out. So then where would you actually put it on the equator? Well, it turns out that we're talking about weather, for example. Then looking at NASA data over the last 150 years, you find that all the storms in the world start off somewhere near the equator and then they spin out to the poles. It's Coriolis force and things like that, which cause these things. So actually by putting it on the surface of the Earth, somewhere probably around here, in this area here, no storms have ever been recorded in 150 years of observations. And you're looking at NASA data, looking at lightning flashes. I've seen this data because these are the kind of people I'm working with. They also see that it's a relatively quiet area. So that's where you would put it. So some of the engineering challenges are being thought of already, but I mean, this is going to occupy minds for decades. So we're not talking about something that's going to happen tomorrow. But again, this is doable. The project plans we're working on with ISEC at the minute, we think this can be done. So we actually started working on these. So you've got project plans with this in place. The architecture has got leads, materials has got leads, operations, safety. There are all people working on this already. We think there's a reasonable chance of getting this done within a 30-year time frame. We start now. And we reckon this could be done for something like $30 billion at the minute. If you consider that with how much is spent 1 year in space, probably $200–300 billion every year is spent on space stuff. You're not talking about a huge amount of money to make sure this thing can be done. Yeah,
and quite a long time frame, but it's expected to be a long time. I think that's quite a soon time frame. Actually, 30 years is quite a.
You'd be surprised with the rate that the technology is progressing at the minute, Liam. We're conservative. We think this could be done faster if people put more time and resources into it.
And I suppose the make or break of it is going to be the ability to produce the graphene. That there's no crux of it. That's the make or break of it on the timescales.
Yeah. Now that's a really good point. To make this graphene here, is a very slow was a very slow process. And I ran a webinar for ISEC last month. So if people go to ISEC's website and look for the recorded webinars, you'll see me talking about this stuff, the latest in materials science. And Liam, I think you and I both know that there's something called a roll-to-roll production method of making graphene on copper foil. And it needs to be made fast. So we can't just use the current lab methods of making graphene, because I ran a calculation a while ago and said for the amount of graphene we're going to need, it would actually take somewhere in the region of about 10,000 years to actually make enough at current speeds. And then, this has just happened a few months ago, a couple of graphene companies came out of the stealth mode, partly because of the pandemic, but one was LG Electronics, which most people have heard of. They've got a roll-to-roll graphene manufacturing process, which already can make graphene at 1 meter per minute. And you and I know that is astonishing.
That's big, that's huge speed, yeah.
Yeah, the rate of production capability that people are working on in this whole area is moving really fast. People are realizing graphene is such an advanced material. Not just Space Elevator that's driving this, it's a whole host of other electronics and other applications, but there is a massive amount of work going on really quickly behind the scenes. And I think that 30 years is probably a conservative estimate. We could probably do it faster.
All right.
Yeah. Certainly in my lifetime, I'm expecting to see at least a test Space Elevator in my lifetime. And I'm a little bit older than 21.
Well, in that case, I should hope to see it in mine then as well. It's
yeah, you're half the age of me.
All right, okay. Okay, well, because obviously I was going to ask about, you know, the cost and everything, but you already covered that one. So we've talked here about using graphene in a tether, you know, for the space elevator, and obviously there's a lot of work being done in the space. That's very clear. It's a very interesting application. Could have big implications down the line. Obviously, a lot of things to overcome in the meantime, but obviously there's a lot of work and progress, you know, being made and has been made over the last few years, and I'm sure there will be over the next decade, which will propel it forward. Now, say we can get these kind of graphene tethers. I'm not even talking on the same kind of, you know, scales, but like just, you know, in general, like graphene tethers, beyond being used in the space elevator. This is going to be a final question for today. What other applications could you actually see like similar graphene tethers being used in? You know, I assume it's not just going to be you can create tethers for the space elevator. I'm sure there's going to be other implications where you can make smaller ones for other applications. So do you have any ideas of where, you know, this could expand out into?
Yeah, definitely. And it's not just tethers, there are other applications as well. I mean, you could probably answer your own question just as eloquently as me, because you know a lot about this stuff. But seeing as this is you interviewing me, then I'll grab it on for a minute and chip in if you've got other answers. You asked specifically about tethers, right? So do you remember I was talking about the fact that when you're standing over that high cliff and you're paying out material and then it breaks under its own weight?
Yes.
You'll notice that most of the buildings in the world are around about 800 meters. When they get higher than that, it's because they stick an aerial on the top or something. And the reason for that is, if anybody who's watching has been in any of these tall buildings, you'll know that you never get from the bottom to the top in one drop for an elevator. You've always got to get out halfway up onto a viewing platform to then get out of one lift or elevator and into another. And the reason for that is that the elevator cables break under their own weight over drops longer than about 400 meters. Well, they're a bit more than that, but with the safety and everything involved, effectively caps a single drop of an elevator at 400 meters. So you need 2 lift shafts if you're going to have an 800 meter building. And the problem is there that the more lift shafts you add, the wider the building's got to be, and you know, it's top heavy, and then eventually you'll get dynamic stability problems with buildings. So buildings at the minute are effectively capped to around about 800 meters, maybe a kilometer, something like that. But you're not going to get any higher because the materials technology for the elevator ropes isn't good enough. However, if we get producing, and you and I can see this happening fairly quickly, you start producing single crystal graphene and multi-layers, and you can put those tethers inside tall buildings. You can make buildings with no height restrictions. Then the height restriction stops becoming the elevator and starts becoming the materials out of which you build the building. So you could build kilometers high buildings, mile high buildings, tens of kilometers high if you wanted to. So that already starts to have massive implications. It takes the sky's the limit, literally, but it takes the height limit off buildings. And think what architects can do when they get hold of this. That's one. Yeah. But you and I know that on the way to making these tethers, that's not the only thing that graphene will do. Once we start making single crystal graphene, this is why LG Electronics is interested in making graphene at high speeds on copper foil, because our mobile phones are one example here. They're covered, the screen here is covered in something that Liam knows very well called indium tin oxide, and it is transparent and electrically conductive. So when you touch the screen, then the computer knows where you've touched the screen and it can sense it. Problem is, indium tin oxide is cheap, but the problem is it's not flexible. So at the moment, our phones are solid and don't bend. And they also break when you drop them, which we've probably all done. If we get single crystal graphene, so we put a single layer of graphene on the surface of that mobile phone instead of indium tin oxide, then you've actually got something which is transparent and electrically conductive, but now is flexible as well. Now we've got flexible phones, but they are flexible displays, not flexible touchscreens. Think of what graphene will do there. That market is $90 billion by most estimates right now, probably a lot more. And so we make phones that you could roll up and bend. Once the technology to make this stuff single crystal large scale has been done. And by the way, that's not science fiction, is it, Liam? Because you and I both know that back in 2013, Samsung made a prototype mobile phone with graphene on the surface, and it worked. So we know it can be done. That's just one application. Ooh, where should we start, Liam, with single crystal graphene? Armour?
Yeah.
Yeah, you make armour that is thin as cling film, saran wrap in the States, food wrap. So it's that sort of thickness, and that would stop a bullet. There are billions of different applications that we should, where do we start?
Yeah.
We've got a fifth materials revolution here, or fifth industrial revolution with single crystal graphene once we start making it at scale, and it's not far off.
Oh, just interesting, and it's a slight diversion. It's just something that you've you mentioned there, especially with the indium tin oxide, and especially like ITO electrodes. I actually wrote something, was it about 3 days ago before filming this, about flexible perovskite solar cells. Oh, yeah. And the issues of using indium tin oxide as the electrode material in like essentially like flexible perovskite solar cells. So is that something else which could, you could filter out ITO for, say, graphene or any application that uses ITO electrodes? Yep.
There are people working on this right now. Some papers produced in the last few weeks where they're looking at using graphene to encapsulate solar cells, which does two things. It's transparent, it's electrically conductive, but it's also flexible, and it's also impermeable. So it can do the job of ITO and more. And so you can have flexible solar cells. The only thing that's holding it back at the minute is the cost of production of graphene. At the minute, you and I know, indium tin oxide is cheap. But it is flexible and brittle. But there's also, solar cells will be everywhere eventually. And then there's a question about the supply chain for indium. And graphene made of carbon, there is, I know you're going to be talking to some people who have discovered a new way of making graphene, flash graphene shortly. But there are ways of making graphene, so it's not dependent on mineral resources in the ground. It could be made in limitless quantities. Yeah. So yes, perovskite solar cells, cheap, flexible, highly efficient, enabled by graphene in the future, and probably not that far off.
I say as well, I'm sure solar cells is actually another aspect that could be utilised in something like the space elevator work for,
Yeah.
for localized powering.
Yeah. The interesting thing about the space elevator, it's not that people don't think it's real or it's science fiction. It's the fact that on the way to make a space elevator, that graphene and other 2D materials have all these amazing properties, that there's all these bright shiny things and billion-dollar industries that get spun off that are distractions making this stuff. I think that is actually going to be the biggest problem that we're facing is how the hell do we get rid of all these billion-dollar distractions so we can focus on making this world-changing bridge to the stars? But it will happen, yeah. And I'm convinced it will happen in my lifetime.
Oh, it's interesting to know, and hopefully it will be. We'll just have to see how things develop over the next few years, next couple of decades. I'm sure you'll have a good track on it. I'm sure we'll be talking about this again in a number of years to come with what's been happening as well. I'm sure that's not too far fetched of an idea. So,
cool.
All right, well, I'd like to thank Adrian from Nixene Publishing and who's also on behalf of the International Space Elevator Consortium as well, for joining me to talk about graphene in the space elevator. Such a different application that we don't hear about often, so it's been great to have a chat with you about it. And thanks to everyone for listening. Hope you found it interesting and it's some new knowledge to you. And until next video, goodbye. Thank you.